Okay, folks. So yeah, I'm afraid we had a bit of a problem with the live stream earlier. The tech kind of let me down quite badly, mainly internet connectivity, but then various other hassles as well. So I'm just re-recording this, and hopefully it will all go a whole lot more smoothly. Just a quick reminder of how things sort of work in these semi sessions. Basically, the questions that we're going to do each day are available at simi.education. And first prize is for you to actually try them beforehand. At the end of the session each day, we will upload the fully worked solutions. Please, if you are finding these useful, please tell your friends. Please like, share, subscribe. Yeah, and just try and kind of spread the word about them. I would really appreciate that. As we've done every time, we're going to dive straight into kind of the formulae that we get given, and they're just two in the case of calculus. The one actually gets provided with the analytical geometry formula. You'd remember that from Friday afternoon's session. And that's just the gradient, and it's the gradient for a line, a straight line between 2 points. It's what we call the average gradient. All right, we'll come to that a little bit later. The other one is the formula for the derivative by first principles. Okay, and we'll talk a little bit more about that just now as well. The next thing I want to quickly just talk you through are the differentiation rules. I've given them to you in three different forms here, in words, in symbols, and then probably the most useful is an example. So just the first one, if we've got a number raised to a power, x raised to a power, and we differentiate that, the power comes down to the front and reduces by 1. So for example, if we differentiate something like x to the 5, it becomes 5x to the 4. Right? The second one, the derivative of a constant, something that doesn't have a variable in it, no x in it, is 0. So for example, the derivative of 8 is 0. If we had to picture the straight line y, sorry, not the horizontal line, y equals 8, it is obviously horizontal. It does not rise. It runs across. It has a gradient of 0. So like all of this maths, it all makes sense. All right, the next one is that if we are adding or subtracting terms, we can differentiate each term and add and subtract them. We can do them each separately. So for example, if we're differentiating x plus x cubed minus 5x, then we can differentiate each of those but separately to get 1 plus 3x squared minus 5. And the last one is that if we've got a number in front of our function, our variable, a constant, we can take that outside and multiply it in afterwards. So for example, the derivative of 5x squared is 5 times the derivative of x squared, or 5 times 2x, or 10x. Right, and I know that you apply those rules kind of seamlessly anyway, but there they are nonetheless. Okay, so what we've got over here, we've got a parabola, y equals x squared, and we've got at the point 1, 1, we've got the tangent line drawn in, and that's indicating the instantaneous gradient at the point A. Right, the instantaneous gradient is 2, and we can see that the equation of that line is y equals 2x minus 1. The blue line is a line joining point A to point B, right? And we can see that as what we calculated over here is the average gradient between A and B. And what we can see is that in fact, as B gets closer to A, that average gradient starts to become more and more like the instantaneous gradient at A. And that's the whole sort of principle of differentiation by first principles. Okay, next up, let's look at this sketch, which is a more general version. We're not dealing with the specific sort of numbers, but we've got a point over here, x, f of x. We've got a point a little bit further away, x plus h, f of x plus h. We are interested in finding the gradient, the instantaneous gradient at x, and that is represented by this dashed red tangent line, all right, and that's f dashed of x, okay? The gradient of the blue line, the average gradient, all right, of the curve between these 2 points, is just our normal gradient formula. So it's the change in y value minus y value over x value minus x value. But obviously, we want h to be small, all right? And we can see that as h gets smaller, the blue line approximates the red line in terms of the gradients more and more accurately. important to note that h cannot be 0, right? Because obviously if h is 0, then we've got a division by 0 on the bottom of this fraction, okay? And we've only got 1 point, and you can't find a gradient with 1 point. Okay, so that's the sort of the underpinning idea of differentiation by first principles. Before we actually try a first principles example, let's just remind ourselves of some sort of key considerations. The first thing is that we actually know the answer before we even start, all right? So make sure we end up there. The next thing is that we must have limit on every single line where h occurs, but never when h has disappeared. So in other words, never on the last line. We must never suggest that h is actually equal to 0. It cannot be. The equal sign always goes on the left of the limit. And then if we have multiple terms, in other words, we no longer have a fraction, we must have brackets around our expression. Okay, let's dive in and try a couple. Right, so here's the first one. Now, the first challenge here is that this thing is not actually in standard form. So what I'm going to do is I'm just going to multiply it out. You'll remember from our algebra session that kind of squaring binomials is something that we're going to do often. So it's useful if we can do it quickly. Remember, we multiply those two numbers in double. So we're going to get 12x plus 9. Okay. Okay, so I'm going to start by just writing down the formula that we actually get provided. It's f dash of x equals the limit h approaches 0 on the numerator f of x plus h minus f of x over h. Right, now we're going to tackle this particular problem, and so it's going to be the limit as h approaches 0. Now we're going to need to put x plus h where all the x's are, so it's going to be 4x plus h all squared plus 12 lots of x plus h plus 9. Now we need to subtract f of x, and f of x is just 4x squared plus 12x plus 9. Now just be careful here, because if we do this, right, we're going to get it wrong, because all of it needs to be subtracted. Safest thing is either to change the sign straight away here, or probably safest still just put brackets in for now. Okay, and this is all over h. But I'm going to do this reasonably quickly, because we know how to square a binomial. We know that when we square x plus h, we're going to get x squared. I'm going to multiply all these things through by 4 as I go. So this is going to be 4x squared plus 2xh times 4, 8xh, plus h squared, plus 12x, plus 12h, plus 9, minus 4x squared, minus 12x, and watching that minus 9 there. Sorry about that. Okay, now we are going to need to factor an h out of the top. And that means that every single term on the top that does not have an h in it must actually divide out, or cancel out rather. So 4x squared and minus 4x squared. 12x and minus 12x. And there I've got my plus 9 and a minus 9. Okay, so what I'm now going to do is I'm going to factor out an h on the top. All right, so I'm going to get lim as h tends to 0. And I get h into 8x plus h. And I want to emphasize very strongly that h is not 0. And because h is not 0, I can divide by h on the top and the bottom. Not cancelling, I'm dividing by h. Right, now this is an important part here, because if we choose, and we don't have to, we could go straight to the answer here, but if we were to choose to write this line out again, in other words, to write out this next line, 8x plus h plus 12, all right? If I do that, I'm actually going to lose a mark. And you might be surprised to hear that, but the reason I'm going to lose a mark is because these brackets are crucial, right? Really, really important that we have those brackets. Okay, it's a similar sort of thing to, for example, sine of 60 plus 2 versus sine of 60 plus 2. These are different things. The limit is applying to the whole lot. Okay, right. As I say, we could have actually left that line out and gone straight to the answer, but if we have it, we must have the brackets. Right, now, let's conclude this. Now, as h gets very close to 0, our answer is in fact just going to be 8x plus 12. Don't go and write plus 0 plus 12. By doing that, you're suggesting that h is 0. Right, h is not 0. Final answer, 8x plus 12. The question was there, 4x squared plus 12x plus 9, and 8x plus 12 is exactly what we expected. Right, so we can move on to the next question with a great deal of confidence, knowing that we've got it right. Just remember those little things about notation. Do not put the equal signs here. Do not leave out limit on any line, but do not include limit once you've applied the limit. In other words, not on the last line when the h has disappeared. And then also remember your brackets, both here and here. Okay, let's dive into the next question and see what it holds. All right, similar one, also differentiation by first principles. I'm not going to write the formula down again. I'm going to dive straight into this one. So f dashed of x is going to be the limit as h approaches 0 of, now I'm going to put x plus h in where all the x's are, minus 1 over x. So this is f of x plus h over here, and this is f of x, right, over h. Okay, now what we're going to need to do is we're going to need to add these two fractions. So we're going to choose a common denominator, and that common denominator is going to be x plus h. So I'm going to make both of these fractions into x plus h, x plus h. Right. Subtracting them. This one already had x plus h on the denominator, so we've multiplied by x, so we must multiply the one on the top by x. This one already had an x, we've multiplied by x plus h, so we must multiply the 1 by x plus h. Okay, this is all over h. Right, our next line looks like this, and in fact what I'm going to do on the next line, to avoid this sort of triple decker fraction, I'm just going to work with this fraction, and then over here I'm going to say divided by h. Right, and you'll see why maybe that makes a little bit of sense just now. So our fraction is x plus h. Later is going to end up being x minus x plus h. Right, and what that becomes is limit as h tends to naught. On the numerator, I actually just get negative h. And on the denominator, I've got x plus h. Right? And instead of saying divide by h, now remember h is h over 1, I'm going to times by 1 over h. And once again, I'm going to emphasize that because h is not actually equal to 0, I can divide the top and the bottom by h. Right, now at this point, I can go straight to my answer because I can now say, well, what is this stuff going to look like when h gets tiny? Right, that we can just ignore, and I'm basically going to get x and x squared on the bottom. I've got negative 1 over x squared. Right, and just to confirm, that is exactly what we would have expected when we differentiate 1 over x, because remember, the derivative of 1 over x, the way we deal with that reciprocal is we say that's actually the same as the derivative of x to the minus 1. And when we differentiate x to the minus 1 using our power rule, the minus 1 comes down to the front. The power reduces by 1. And then if we write this with a positive exponent, bingo, we're there. Okay, right. Onwards and upwards to the next question. Question 3 is around using the rules of differentiation. And I like to say that before we can differentiate something, it must be flat. And by flat, I mean no fractions, no brackets, no fractions, and no surds. Okay, so we're going to look at how we eliminate all of these things. You'll remember from the algebra session on Friday, that Thursday rather, last week, that the way we sort of simplify fraction is by factorizing. Okay, so we're going to tackle this one by trying to factorize. So clearly 2 is a common factor on the bottom, so we get 2x plus 2. So we're expecting that x plus 2 will be a common factor in the numerator. I think everyone will be happy with the fact that we needed x squared there, and that will give us our x cubed. At the back, we're going to need a plus 9, and that will give us our 18. Now, if we were to multiply these fractions at the moment, as they, sorry, those two brackets rather, as they stand, we would actually get 2x squared. And I'm going to show you where that's going to come from. It's going to come from this 2 that's going to come from this 2 multiplying with this x squared, 2x squared. I want a total of 5x squared. Okay, and so I need to introduce another 3x. So what I'm going to do is I'm going to write in here plus 3x. That is going to become 3x squared when it multiplies with that, and that's going to give me those 5x squareds. Just as a final check, x's will come from x's from this bracket with numbers from this one, there's 9x, or numbers from here with x's from here, there's 6x. Okay, so it's all good. Now we can divide and divide. Right, so Paul, it's still not flat, but in fact we can write it now as y equals half x squared plus 3 over 2x plus 9 over 2. And we can now differentiate. It's now flat. And we just x, we get plus 3 over 2, and the derivative of 9 over 2 just 0. Okay, right, the next one, I've picked these next two notations because they're really, really important. Sorry, just to go back here, notice we only called it dy dx when we differentiated it. Right, now what these two notations mean is work out the gradient of, okay, work out the derivative of. So this is not flat and ready to go yet. So if I change this to x to the 7 over 5, remembering that the number outside goes on the denominator, the number inside on the numerator, I'm going to write that 4 over x cubed as 4x to the minus 3. Root 2 hasn't actually got a variable in. I don't need to change that to 2 to the half. I'm not differentiating it. It's just a number. However, what I've written so far is problematic because this was saying find the derivative of this stuff, and I haven't done that yet. So I still need to write dx and put all of this in a big bracket. I'm going to differentiate all of this stuff. Now at this point, I'm going to differentiate, and I get 7 over 5 x to the 5th minus 12x to the minus 4, and the derivative of root 2 is just 0. I don't write the dx anymore because this thing is now done. I think my question did ask for positive exponents, so I'm just going to write that other exponent as a positive exponent. So it's going to be minus 12 over x to the 4. Okay. Right, the next and last one of these. Here we've got a little trick that we employ where we split the fraction up. So what I'm going to do is I'm going to write this as d by dx. Okay, and I'm going to break this fraction up into 4x to the 9, 2x to the 7, plus 5x over 2x to the 7. Okay, and what we can see is that if we were adding these two fractions, we'd be able to put them together. In other words, we'd be able to go from the second row to the first row. We can just as easily go from the first row to the second row. Right, and now I'm still going to leave it as d by dx because I haven't differentiated it yet. This one becomes just 2x squared, which is kind of nice and flat. This other one becomes 5 over 2, and I'm going to separate that coefficient out. X to the, remember there's a 1 there, x to the minus 6, an exponent law idea. Right, now I'm ready to differentiate, and in fact I'm going to differentiate, and I get 4x plus 5 over 2. Sorry, now I'm going to multiply. This is going to become negative x to the minus 7. Right. The negative 6 times 5 over 2 becomes negative 30 over 2. Right. There it is. The last thing I need to do, though, is just make sure that I've got my answer with a positive exponent. So that's going to be 15 over x to the 7. Okay. And that's how that one looks. Right, now, the whole point of finding derivatives is to sort of learn something about the behavior of functions. Okay, and so this question says determine whether f of x is x minus root x is increasing or decreasing or stationary. Well, if we work out its derivative, then we will be able to, we'll know, right? I'm not differentiating it yet. I'm writing it into standard form, to like flat form rather, okay? And now I'm ready to differentiate it. So in fact, f dashed of x is actually going to be 1 minus x to the minus a half, right? And now what I'm going to do is I'm going to put 2 in. And what this notation means is the gradient of f at 2. Right, and when I put 2 into here for the x, I get approximately, I think it was about 0.6 or something. Yes, about 0.65. Okay, now that is positive. And because it's positive, it means that we have a gradient sloping uphill, which means that the function is increasing. Positive gradient means that the function is increasing. Okay, so we've successfully answered that question. Okay, here's another one, very similar, right? What we're going to do, it says, where is this function increasing? So what we're going to do, we're going to work out the derivative. And we get 6x squared plus 10x minus 4. We want that to be bigger than 0. Right, now this is a quadratic inequality, the likes of which we solved in the equations video, right? Let's divide everything through by 2, and we get 3x squared plus 5x minus 2 is bigger than 0. Right, now we're going to try and factorize this. It factorizes very easily, actually, because 3 and 2 are both prime numbers, so there's not a whole lot of options. It's got to be 3x and x, and it's got to be 2 and 1. In order to get 5, I'm going to put the 2 here, which will give me 6, and I'm going to put the 1 here, and I'm going to make this minus 1 and plus 2. Right. So what we've now got, if we had to picture this thing as a graph, right? Basically, so what I'm graphing now is I'm graphing the gradient, all right? It's a parabola. It's a happy parabola, what we actually refer to as a concave up parabola, all right? In other words, it's kind of this way up. But anyway, this is negative 2, and this is a third. And we are asking ourselves, where is this parabola bigger than 0? Now, it's bigger than 0 outside of its roots. So in other words, our final answer here is that x will be less than minus 2, or x will be bigger than a third. Okay. Okay, and that information equips us to answer this question. This is asking where this thing is concave down. Now, concave down, remember, means concave down looks like this. It means like a frown. And it's also where our second derivative is negative. Just on the other side here, I'm going to draw the other one, which is concave up like a cup, right? Concave up like a cup, right? And at all along that curve, the second derivative is positive. Okay, right. So let's get to tackling this problem. Don't panic that it's got an x to the 4 and you don't know what that graph looks like. Let's just differentiate it a couple of times. The first derivative will be 4x cubed over 12. Notice the 12 is just a constant on the bottom. It'll be 3x squared over 6. It'll be minus 2x, and it'll be plus 8. Okay, now we're going to differentiate that again. We're going to find the second derivative. And when we do that, we actually get 12x squared over 12, which is obviously just x squared. We get 6x over 6, which is just x, and we get minus 2. And we want the second derivative for concave down, we want the second derivative to be negative. Once again, we are solving a quadratic inequality. Let's just quickly factor it. X plus 2, x minus 1 is less than 0, right? And again, if I like to picture the graph of what that actually looks like, well, it's a concave up parabola. It's a happy parabola, concave up, right, with x-intercepts of 1 and negative 2. And now we're asking, where is this thing negative? Well, it's negative in between those two values. So negative 2 less than x less than 1. Okay, that's the deal with that one. Okay, on to question 7. And I apologize, the first draft of these questions talked about the y-intercept of this graph, which is completely impossible. It doesn't have a y-intercept. Just to visualize what this function looks like, all right, it's actually a hyperbola that's been dropped down, all right, by 2. Functions video and live stream still to come, which I'm looking forward to. But this asks us to find the equation of the tangent somewhere through there at the x-intercept. Now we can find the x-intercept very easily by letting y be 0. All right, so in this equation, we're going to let y be 0. It equals 6 over x minus 2. And add 2 to both sides, we get 2 equals 6 over x. We're going to multiply both sides by x to get rid of the fractions. We get 2x equals 6. We're going to divide both sides by 2, and we get x equals 3. Right, so this point is actually the point 3, 0. Now we need to find the gradient of the tangent line. So we're going to need to differentiate our function. The function's not flat. When I write it flat, it's actually 6x to the minus 1 minus 2. I'm now going to differentiate it. dy dx is going to equal negative 6x to the minus 2, right? Which is also negative 6 over x squared. Right. When I put 3 into this derivative, I get negative 6/9. So at x equals 3, the gradient is actually equal to negative 6/9, which simplifies to negative 2/3. Finally, I need to use either y equals mx plus c or y minus the y value of 0 equals the gradient x minus the x value of 3. Okay, and I get a final answer here, all simplified as y equals negative 2x plus, sorry, negative 2/3 x plus 2. Okay. Just to show you, let's just check that out. If I type that in, y equals negative 2x over 3 plus 2, there we can see the tangent line at the x-intercept. Okay, this next question, this function has two tangents which are parallel to this line. Find both of their equations. Well, let's have a look. This line is not in standard form. It's 2y equals 8x plus 16, right? Which obviously means that y equals 4x plus 8. So in fact, the crucial thing here is that the gradient of this line is in fact 4. Right. So now what we're going to do is we are going to work out, where does this curve have a gradient of 4? So let's differentiate it. F dashed of x equals 3x squared minus 2x minus 1. I'm not trying to find the gradient at 4, so I'm not putting 4 in for the x's. I'm trying to find where is the gradient equal to 4. This equation simplifies to 3x squared minus 2x minus 5 equals 0. It factorizes. Once again, 3 and 5 are prime, so not difficult to factorize. It must be 3x. It must be x. It must be 5 and 1. I don't want to put the 5 here, otherwise I'll get 15. So 5's going there, 1's going there. I want negative 2, so 3x minus 5x plus 1. Okay, so in fact, the x values are actually x equals 5 over 3 or negative 1. Right? I now need the y values of these points of contact. I'm going to get the y values from this. All right, because remember, f of x is just like y. I sub those in, and we get the following. For 5 over 3, we get and for negative 1, get negative 2. Now I want to find the equations of these two lines, the equations with of two lines, both with a gradient of 4 passing through each of these points. Okay, so I'm going to do the first one is y minus the y value, so it'll be y plus 2 equals 4x minus the x value, so it'll be 4x plus 1. This actually comes to y equals 4x plus 4 minus 2, just 4x plus 2. And the other one, y minus the y value, so y plus 22 over 7 equals 4x minus 5 over 3. And this one simplifies to y equals 4x minus 202 over 27. Not very nice numbers, but there they are nonetheless. Two different tangent lines. Okay, there's the curve actually. Let's just type those two equations in about two tangent lines. So 4x plus 2 was the one, and we can see it is indeed a tangent, right? The other one was y equals 4x plus, I don't think it was plus, I think it was minus 202 over 27, parallel to one another. Okay, this next question is interesting. It's a sort of level 4 question, a more difficult question. It's asking us to find B and C. Now, just as a little sort of alert, whenever you're asked to find two variables, simultaneous equations are very, very often involved. We're going to see that tomorrow in our sequences and series work as well. Right. So the first thing is that it says that this is a point on the graph. Now, this is a point on the graph. That means that f of 2 is equal to minus 3. That means that when we put 2 into this equation, we're going to get 2 cubed. So when we put 2 into this equation, we're going to get 8 plus 4b plus 2. That will equal our y value of minus 3. Right. This can sort of tidy up a little bit to maybe 4b plus 2c. I've got a total of 13 on the left-hand side, which if I subtract, I get minus 16. Now, this is an equation. It's really nice. Unfortunately, it's got two variables. So what we're going to do now is we're going to look at what else we were told here. We were told that not only is this a point, but it's a local minimum. Now, at a local minimum, we know that the gradient is equal to 0. So we know that, in fact, f dashed of 2 is equal to 0. Right. I'm going to just, up at the top here, I'm just going to work out the derivative of f. All right, f dashed of x is actually 3x squared plus 2bx plus c. Okay? And we now know that when we put 2 into there, we get 0. So putting 2 into there, we get 12 plus 4b plus c equals 0. And that is a second equation in two variables. So we've now got two equations in two variables. Okay, I've spotted that both of them have got 4b here. Right, so I'm going to rewrite equation number 1 down here again, the blue one. I'm going to write it again, but I'm going to write the 4b's kind of lined up over there. Right, I'm going to write the 2c's lined up over here. And I've got minus 16. Okay. I haven't really achieved anything by doing that, but I'm going to write the black one down now underneath here as 4b plus c, and I'm going to subtract 12 from both sides, just so they're both in the same sort of format as such. Now, because I've got the same number of b's, I can subtract these two equations. And when I subtract them, I actually get no b's, which is a major coup, and I get 2c minus c is just c. I get minus 16 minus 12. That's minus 16 plus 12. I should get c equals minus 4. If c equals minus 4, I can sub it in anywhere, all right? And in fact, I get b. If c is minus 4, this will become 12 minus 4. I'll get 8, which means that b must be minus 2. And there's Okay, so this next question now is asking us to find the average gradient, and it's in bold there, the average gradient. Remember, average gradient's got nothing to do with calculus, actually, right? If we had to draw get a rough idea of what 2 to the x minus 8 looks like, it's actually an exponential graph that's sort of been dropped down by 8. This asymptote is at y equals minus 8. And we're being asked to find the average gradient of the function between its intercepts. In other words, between these 2 points. Right, obviously we find this point by letting x be 0, and in fact we get 0, negative 7. And we find this point by letting y be 0, and we get 3, 0. The average gradient is the gradient of that blue line, and it's actually, the function is risen 7 and run across 3. So there's our answer for the average gradient. Okay, not to be confused, but you don't average two instantaneous gradients, all right? That does happen to work on a parabola, but only on a parabola. So don't do that. Rather just use the 2 points. Okay. Right, the next question, question number 11, looks at a function and then asks us to solve various things. And the first thing it says is, where is f dashed of x less than 0? Now, f dashed of x, remember, is the gradient, and the gradient is less than 0 when the graph is decreasing, when it's going downhill. And that happens in between the two turning points. In other words, from negative 1, less than x, less than 4/3. Okay, negative gradient, function decreasing. The next one asks for, where is the second derivative equal to 0? Well, remember the second derivative is negative when the graph's concave down, positive when the graph's concave up, and 0 at the point of inflection. So this is just going to be x equals 1/6. Okay. The next one is interesting. It's asking us for the x value times the function value to be negative or 0. Now, the way a product is negative is to have one of the factors positive and one negative. One positive and one negative. Now, we're talking about the x values and the function values. Now, remember, f of x actually means the y value of function f. Right. So if we want positive x values, I'm going to answer this question actually over here on the left-hand side where I can actually see what I'm doing here. So one possibility is to have positive x's, all right, and negative y's. Now, positive x's mean being on the right-hand side of the y-axis, and negative y's mean being below the x-axis. So where are we on the right-hand side of the y-axis and below the x-axis? And that's from 1/2 to 2. I can include 1/2 and I can include 2 as well, right? Because those values would actually give 0 and the thing is saying less than or equal to 0. Alternatively, and I'm just going to change pen color, I could have negative x's with positive y's. Now that negative x's look like points on the left-hand side of the y-axis, and positive y's look like points above. Right. So here we would be talking from -2 less than or equal to x to 0. Okay. So these, in fact, are our two answers. That one there and this one here. Okay, the next and last one of these, we want a positive product. Now, the way we're going to get a positive product is both things positive or both things negative. Once again, I'm actually going to answer it up here. So this is asking for f dashed of x times f double dashed of x. Right. F dashed of x, f double dashed of x. First up, I'm going to look at them both being positive. Right. If they're both positive, let's talk about what that looks like on the graph. A positive gradient means that the graph's going uphill, right? And the positive second derivative means concave up. So in other words, we want, where's the graph going uphill while it's concave up? Uphill and concave up. And remember, it's only concave up from the point of inflection onwards here. And it's only, in fact, going uphill from 2 onwards. So the answer to this one is x bigger than 2. This time we're not including 0. So there it is. That's all that is. The other possibility, though, is for them both to be negative. Right? And that a negative times a negative. And that would look like downhill, negative gradient, downhill, and negative second derivative, concave, down. Okay, and so let's have a look. It's concave down here, all right, up to the point of inflection, but it only is going downhill from -1. So in fact, we're going to go -1 less than x less than 1/6. Those are the places where it is both downhill and concave down. Okay, I hope that made sense. Right, now this next question, and it's kind of highlighted for us that the graph of the derivative of f is drawn. This is not the graph of f. This is the graph of the derivative of f. And it says, what would be the coordinates of the stationary points of f? Right? Now remember, the stationary points of f are where they will occur where f dashed of x equals 0. And f dashed of x is 0 at -7 and at 3. So -7 and 3. All right. Now let's look at what the nature of these is. In other words, which one is a maximum, which one's a minimum. To the left, okay, so we know here's an x value of -7, all right? And we know that the gradient is 0 at that point. So the graph's kind of flat just for an instant there. Now, less than -7, in other words, to the left of -7, the gradient is actually negative, which means that it's actually coming downhill. After -7, the gradient becomes positive. So in other words, the graph's doing something like that at the x value of -7, right? Which means that at x equals -7, we've actually got a minimum turning point, right? What we call a local minimum, right? At x equals 3, if we look here to the left of 3, in other words, just before we get to 3, remember at 3 the gradient is 0. Just before we get to 3, the gradient is bigger than 0. All right. So in other words, it's positive. Sorry, it's positive. The function's increasing, and then after 3, it starts to decrease. So this is a maximum. Right, then it asks us for which values of x is f of x concave down. Now, for f of x to be concave down, we need the second derivative to be negative, right? Now remember that this is the graph of f dashed of x. The gradient of this graph will be achieved by finding our second derivative. So what we're really asking is, where does this graph have a negative gradient? And it has a negative gradient after the turning point, right? And the turning point by symmetry of the two x-intercepts, the turning point's actually at -2, right? So this graph is actually concave down after x is -2. In other words, x bigger than -2. We can actually also see it, another way of looking at it is to say that this graph, the derivative was a parabola, so the original graph must have been a cubic function, and we've established that, in fact, the graph had a minimum first and then the maximum, right? So the basic shape of the graph is something like this. Minimum first, then maximum, all right? And there's our point of inflection, and notice the graph is concave down like a frown after the point of inflection, concave up beforehand. Okay, and that brings us to the end of that question. Right, this next question, Sibonelo takes a piece of rope. This is an optimization question. Both of the next two and the last two are. He takes a piece of rope 100 centimeters long. He cuts it into two pieces and makes a square with the one piece and a circle with the other. If the length of the side of the square is x, determine an expression for the total area enclosed by the two shapes. Right, well, firstly, the area of the square is going to be very straightforward. It's just going to be x times x. Now, the area of the circle, we don't want to introduce another variable. The secret to optimization questions is always just to have one variable. And so what we're going to work out is, how big is this circle? How big is it in terms of its radius, its circumference, its radius, and its area? Right? So what we're going to work out is how much rope is actually left. Okay? He's used, in fact, if we picture the square, he's actually used x, 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 x. He's used 4x. So what he has left is 100 minus 4x. And with that, he's going to make a circle. Here's this circle. Circle. Here's the circle. Right? Let's try not to draw it over the x squared this time. Right, there's a circle, not very well drawn. But that 100 minus 4x actually represents the circumference of this circle. Now, the formula for circumference of a circle is pi times diameter, or 2 pi times radius, right? So we, in fact, know that the radius is actually the circumference divided by 2 pi. So, in fact, the radius of his circle is going to be the circumference, which is 100 minus 4x, divided by 2 pi. All right, now remember that area of a circle is pi r squared. Before I do that, I'm actually just going to simplify this because 100 over 2 is actually 50, all right? And 4 over 2 is just 2. So this is actually 50 minus 2x over pi is the radius. So the area of the circle, it's going to come across here, and I'm going to write it. The area of the circle is actually going to be pi times the radius squared. Now notice the radius is 50 minus 2x over pi. All right, that's the radius squared. Now I could simplify it, and in fact I'm going to simplify it somewhat. I'm going to square this out. How many times have we squared a binomial already in these video series? 50 squared, 2500. That times that doubled, so minus 100, in fact minus 200x, plus 4x squared over pi squared, right? And then the last little bit of simplification here is that we can divide one of the pi will divide with one of the pi's on the denominator. So we're going to get 2500 minus 200x plus 4x squared over pi. Right, so that's the area of the circle. Part B of the question says determine x if Sibonello wants the total area to be as small as possible. Right, now the secret to this is to get an expression for the total area. So the total area, which I'm going to call big A, that's going to be the area of the circle, which we've got here, 2500 minus 200x over pi. So 200x plus 4x squared all over pi. That's the area of the circle plus the area of the square. Right. Now, if we were to draw that as a graph, I'm not sure what it looks like, but it's got a minimum value at some point, and at that point, the derivative will be 0. Okay, so I've drawn that slightly off the screen. The derivative will be 0 at that minimum value. Okay, so now let's differentiate it. A dashed is going to be, now this, I'm going to break it up into, this is going to be 2500, sorry, I'm not going to differentiate it yet. I'm going to get it flat first. A is going to be 2500 over pi minus 200 over pi times x plus 4 over pi times x squared plus x squared. Right, now we're ready to differentiate it. The first term is just a constant, so that will be 0. This will be negative 200 over pi. This will be plus 8 over pi x. And the last one will be 2x. And we want that derivative to be 0. Okay? So, now we're just trying to solve this. Let's add 200 pi to both sides. Sorry, 200 over pi to both sides. Let's factor out the x. Remember that strategy of getting our x's in one place through factorizing. And now let's divide 200 over pi over 8 over pi plus 2. And what we end up with is, in fact, 14 centimeters. Okay, so the smallest possible area he can enclose is if he actually takes 14 centimeters for each. Now I'm going to show you a little visualization of this, and there it is. We can see that the minimum's at 14. What's interesting, I put the red lines are the sort of boundaries of the problem, because obviously he could take 0 for the sides of the square. If he takes 0 for the sides of the square, he actually only makes a circle, right? And in fact, that's the largest area he can contain, right? If he takes 25 for the sides of the square, in other words, he uses all 100 centimeters on the square, then he doesn't have a circle at all, and that's the area that he ends up with. And an important idea which will be emphasized at university is that maxima and minima, in other words, maximum values and minimum values, they either occur at end points, right, or they occur where the gradient is zero. Okay. And for school calculus, we tend to only really worry about where the gradient is zero. But in fact, in this, you can see that the maximum area is actually not achieved at a gradient of zero. It's actually achieved at an end point of the interval. All right, and on to the very last question. This is a classic sort of optimization question. What we've got here, we've got a triangle drawn as shown. This vertex G is on this graph of negative 2x squared plus 4. Now, a really, really important idea here is that if a point lies on a function, then it must have the form of x negative 2x squared plus 4 if it lies on this particular function. Every single point that lies on this function, the y value is the x value squared multiplied by negative 2 and added 4. So, for example, if I said to you, well, what's the y value if x is, say, 5? Well, what you would do is you would go negative 2 times 5 squared plus 4, right? But that would apply equally if I said to you, well, what if x is 3? We'd go 3, negative 2 times 3 squared plus 4. And if x is x, we'd go negative 2 times x squared plus 4. Right. Now, this point over here, because it's a right angle triangle, h is obviously x, same x value, 0. Right. What we are trying to optimize here, trying to maximize, make as big as possible, is the area of this triangle. Area is half base times height. So, in fact, the area of this actual triangle is going to be half x times negative 2x squared plus 4. Right? We want to differentiate it, but it's not flat at the moment. When we multiply these two together, we get negative x squared plus, negative x cubed, in fact, plus 2 . How are we going to differentiate it? We get that a dashed is negative 3x squared plus 2. I want that to equal 0 for a maximum. I'm going to now solve that. So negative 3x squared equals negative 2. X squared equals 2/3. And so, in fact, we get x equals about 0,817. And that's the value of x that gives us the maximum area. Okay, so let's just take a look at what's happening here. As we drag this point along, you can see that the area, there's the area written there. It's getting bigger and bigger. Remember, we worked out that it was going to get to a maximum at about 0,8 something, right? And you can see it's still getting bigger, still getting bigger, still getting bigger, right? And now you'll see after I go past here, it starts to get smaller again, right? So that value that we worked out, I can't remember what it was, something like 0,81 maximum area occurs. Okay, guys, yeah, sorry, today's session's been a bit fraught in terms of the live stream not working. Tomorrow we're doing sequences and series and really looking forward to seeing you all online there. Please remember to like the videos if you do like them. Don't like them if you don't, but if you do, please do. And please remember to share and tell your friends. Great. Enjoy the rest of the day.